Again, and I was trying to think of something to video, so I thought I'd do a video on RF attenuators, um, why you need them, um, demonstrate some on the spectrum analyzer, and in front of me I've got a collection, some of which are professional ones and some of which are homemade, and there's a big one behind which is a big power attenuator. Right, well, basically, why would you need an attenuator? Well, if you've got a big signal, or any signal, and you want to attenuate it by a known amount, you use an attenuator. And you might want to, say, measure the output of a transmitter on a spectrum analyzer, like this little radio I've got here, Bofang transmitter with a 4-watt output. Well, there's no way I could connect that to my spectrum analyzer and transmit into it. That would be the end of the spectrum analyzer. So I'd stick it through a power attenuator, and ideally this big one over here, because that's got a 100-watt rating and 30 dBs of attenuation. And then I can check the spectral purity of the radio. But anyway, they come in basically two types. You've got a pi attenuator and a T attenuator, and it really depends, if you're making them, on how convenient it is to get the right resistor values. And the pi is called a pi because it resembles the letter pi, and T resembles the letter T. But in this example, for a 10 dB attenuator, you're going to need two identical input and output resistors of 96.25 ohms and a series resistor of 71.15 ohms. Now, you ain't going to buy those resistors off the shelf, so if you want to make something like this, you've got to try and parallel or series resistors to get as close as you can to those values. And there again, the bottom example is for a 20 dB attenuator, and for the pi attenuator you need a 61.11 ohms on the input and the same on the output, and 247.5 ohms on the series resistor. But yeah, you can calculate all this if you really want to. There's a hideous calculation to work out all these values, but these days you can get calculators on the internet that'll do it all for you. So I've made a few attenuators over the years, and we'll have a look at them in a minute. But the first one I'm going to show you is one that I've got out of an old spectrum analyzer years ago, and it's made by Nada, which is a really, professional company when it comes to attenuators, and it's 10 dB, and it covers the range DC to 6 gigahertz. So I can be pretty sure that that is a high quality flat attenuator over that frequency range, and I'll show you that on the spectrum analyzer later. But other ones I've made, back in the early 80s, I built a 10-watt transmitter, and I wanted to measure its output on a spectrum analyzer. So I built this. It's a 20 dB, roughly 10-watt attenuator, and I'll take it apart in a minute and see what's in it. But and another one I built, which is same sort of thing, but this one's a 10 dB attenuator, roughly 10 watts power rating. And what else have we got? We've got other ones I've made. This one is one I made a couple of years ago. It's just a BNC socket and a BNC plug, chopped up, joined together, with a attenuator network inside it. using surface mount resistors. Now, when you're working at high frequencies, lead resistance and also capacitance has an awfully big effect on attenuators. So you want to minimise that to keep that to the absolute minimum. That's where surface mount resistors are very handy when making low power attenuators. So what have we got? We got another one here, 6 dB. That's the same as the last one in construction, and another 6 dB. And I use those as I'll show you later. For what else we got? The last one here is this came out of an old spectrum analyzer that was scrapped. We used to have this scrap heap at work where I used to work, and I used to go out there and get all this old equipment out. I think it was a very old HPE spectrum analyzer in there, probably from the 60s, and it had this, you know, high quality attenuator in it, which was 6 dB at the time. Well, I didn't really have any particular use for a 6 dB attenuator, so I redesigned it to be 20 dB. And the last one I'll show you is this big one. Right, now this is a nice one because it's a 30 dB attenuator and it's rated at 100 watts. And I picked this up at a radio rally about 15 years ago. I don't think they knew what it was because I got it for like 10 quid, which is bugger all for what it's worth. I mean, to buy something like this new would be hundreds, and I think its ratings are yeah, 100 watts, 30 dB, and it's specified to 2 gigahertz, which is pretty impressive. It's got all the specifications on the bottom there, as you can see. So this is ideal really for testing high power transmitters, because if you put like 100 watts in one end, you'll get 100 milliwatts at the other end, or in dBm terms, 100 watts would be 50 dBm, and at the other end you'd get 50 minus 30 is 20 dBm, which is just about acceptable to go into my spectrum analyzer, which has got a rating of 30 dBm input maximum. Even so, I wouldn't really want to put 20 dBm into it, so I'd probably put another 10 dBs in line on the output of it, just to be absolutely certain. So I think I'll go over to the spectrum analyzer now and show you some of the homemade ones, or maybe I'll take apart one of my power ones and show you how I built it. Okay, this is my homemade 20 dB, roughly 10 watt attenuator. I'll just take the top off it, and you can see how it's constructed. Basically, it's a lot of resistors on the input to get the maximum power rating, and then these are connected on the input pin and they go down to earth, so that would form the first part of the pi attenuator. And when it will focus, doesn't want to bloody focus as usual. Anyway, these resistors have all various combinations to get 61 ohms or whatever it was, but and then you've got series resistors to get the 247, or as near as possible to that. I think it's actually 240 I've got there, because I've got two 240s in series, and then another two 240s in series, and then in parallel to get 240. So it's not exactly what it should be. It's which is 247.5. That would be the ideal value. As you can see, the output one is a 62 ohm, which is the nearest I could get to 61.11, and that one looks like it's been a bit burnt, probably because I plugged it in the wrong way around. But you know, I built this like 30 years ago, and it was never intended to go that high in frequency. and also I didn't really optimize the values, so it wasn't a perfect 20 dB attenuator. But in a minute I'll stick it on the spectrum analyzer and you can see how good or bad it is at various frequencies. Okay, I've got the spectrum analyzer connected up, and what I'm doing is I'm sweeping between 0 and 2 gigahertz just because I can, because this goes up to 2.1 gigahertz, and I'm feeding the tracking generator output into the input of the spectrum analyzer so I can do frequency response tests on these various attenuators. And I'm just trying to get this right. Okay, so as I said, I've got this set up, and if I go to tracking generator and renormalize it, you see I get a flat line, and if I press marker, it obviously will give you a 0 dB attenuation because I've just got a cable going between the output of the tracking generator and the input to the analyzer. So if I stick a known good attenuator on there, I use the NADA because I think that's going to be pretty reliable. So I'll just connect that in series and you'll see what the result is. So in theory we should get exactly 10 dB, but it's a bit wiggly, as you can see. It goes up and down. Now I don't think there's anything wrong with the NADA attenuator. It's rated at DC to 6 gigahertz, and if I go right up the top here, we're going to have significant error. It's right down, it's 10.7 to 3 dB loss, which I don't believe. I believe there's basically an impedance problem on the output of the tracking generator and the input of the analyzer. After all, it's quite a big range of sweeping over, and you can't expect perfect output impedance and input impedance. You can't expect it to be exactly 50 ohm. So what I've done to overcome this problem is I made up a couple of 6 dB pads, which is the ones I showed you. So what I'm going to do now is insert those, one in the output tracking generator and one on the input of the analyzer, and we'll see what effect that has. Okay, I've got those two 6 dB pads in now. Of course, the disadvantage of doing this is I'm losing dynamic range. I've added another 12 dB in basically. But anyway, I now need to renormalize the tracking generator, which I'm doing. So I've got a flat line again. Press marker, and it's completely flat with just a cable going between the output and the input. So now I'm going to stick that NADA attenuator back in, and I hope it's going to be flatter than it was. Okay, well that's considerably flatter. I mean, right up at 2 gig, 10.15. That's much more reasonable. Yeah, it's basically within 0.1, 0.2, 0.1 dB all the way across. So that's what I've devised now as my test method, is to put those two pads in, and that seems to give better results. So I just put in one of the homemade ones. Okay, I'm going to now put in this homemade 20 dB attenuator. We'll see what that looks like. It won't be as good as the professional one, of course. Okay, and as you can see, it's not great, but it was never intended to work at really high frequencies. If you go down the bottom end, which is where I was using it, it's still fairly good, for a power attenuator that was built like that. You've got tremendous problems with stray capacitance in that box and inductance to the wires and whatever. But you know, 100, let's say 100 megahertz roughly, it's 19.5 dB. That's reasonable, and I think it's more to do on the low end to do with the inaccuracies of the resistors that determine how good it is. But if I go up to, let me see, marker 1 gig. Yeah, 1 gig it's minus 21. It's still not too bad, 1 gig. But right up here, it's just an absolute disaster. We're going right down to minus 35, which is unusable, basically. But that's what you expect with something like that. Anyway, I'll just try the other one, which is the 10 dB one, which was similar. Okay, now I've got the 10 dB attenuator in, which was exactly the same basic build as the 20 dB one. And I'm going to put my marker down at 100 megahertz. That's pretty good, you know, that's minus 10. Exactly, so that I can't complain about that. And as you go up, as you can see, it starts to get a bit more inaccuracy. Like, yeah, 930 megahertz is minus 12, so it's fairly unusable up here. And like the last one, it's a complete disaster. It's actually minus 20 at 1.6 gigahertz. But that's to do with the construction methods in that box, and it was never intended to go to those frequencies. I wasn't going to use it above 100 megahertz, those two I've just showed you. So I'll go on to another couple I've made. Okay, so this is a little 10 dB one I made using surface mount resistors, which is going to have less problems than using ordinary wire ended resistors. And it's just two BNCs. Well, it's a BNC plug and a BNC socket soldered together with the tiny little pi attenuators inside it. So I'm just going to connect that one up. So as you can see, that one is pretty good. I go down to 100 megahertz. I'm getting exactly 10 dB, and I did that to get. I got that accuracy by basically paralleling resistors till I got exactly these figures of 247.5 and 61.11 for the, no, that was for 20, but no, for the 10 dB it's 96.25 ohms and 71.15. I managed to get in very, very close to those values by combining in parallel surface mount resistors. So 100 megahertz, yeah, it's perfect. So, and as you go up, it is still pretty good. I mean, it's still usable at a gigahertz. It's 0.4 dB out at gigahertz. So that's pretty impressive. And yeah, still not bad all the way up. All the way up to, it gets just a bit worse at 2 gigahertz. It's roughly 0.8 dB out at 2 gigahertz. So it's not bad really, considering it's home construction. And then the last one I'll show you is another one I made. The last one is one I wanted to try and make the perfect attenuator, as close as I could get to a professional one. And it took me quite a few tries to do this. And after I've shown you how good it is, I'll take it apart and show you what was in it. Okay, the last one is this one. Originally it was a 6 dB when I got it out of the old spectrum analyzer, but now it's a 20 dB, and I'll just wire it in. I have to use adapters on this because it's N-type to N-type. Lots of adapters. Now we get a little bit more noise now because we're getting down into the whatever one. Let's put to 100 megahertz. Okay, 100 megahertz is perfect. As you can see, that's not too far off as good as that NADA was. I mean, 1 gigahertz is still perfect, and it just starts to get a little bit inaccurate 1.4 gigahertz, but you know, it's still pretty usable even with that frequency. As we go up to 2 gigahertz, it's half a dB out, and that was the best I could achieve using home construction techniques. I think it's pretty impressive, really. Now I'll just take it apart and show you how I did it. Right, this is the attenuator. It just screws together, and inside we've got a little barrel. Inside that little barrel is the actual circuit I built. Let me move this camera about a bit. I might have to zoom in on this. And it is pretty small. I'll just get the actual circuit board out. No, it doesn't like coming out that way. I have to push it out the other way. So here we have a tiny little circuit board, and it took me probably 3 attempts to get this as good as it is. The first attempt I did was I just got the PCB material and cut it away with a knife, and so it wasn't particularly sharp edges on the cuts or anything, and the center conductor that connects the various elements together wasn't very good either, so in the end I etched it. And what I did was, because I originally tried making a 20 dB attenuator in one pi unit, I found that was not a very good way to do it. It was better to use 2 10 dBs in series, so that's what I've done here. I think the problems were when you were working with values like 247 ohms as the series resistor there on a 20 dB attenuator. It was just the capacitance across the surface mount resistor was having a considerable effect on the actual attenuation. So I went to 2 10 dBs in series, but as you can see, it's quite a feat, quite an achievement to produce something this small, and that works so well. But I like playing around with this sort of stuff. It gives me something to play with. It's better than being out on the streets. So anyway, that's my little video on attenuators. I hope you enjoyed it.